welcome everyone to Science Society, and of course, a special welcome to you, Paul. And before we start, let me give the audience a short introduction, and then we'll go from there. I know people will keep coming in, but I think we can just start, and once we are done with the interview part, probably everyone should be here, or most people should be here. Great. So, Professor Paul Cassak, he is at in the plasma and space physics theory and computation field in the Department of Physics and Astronomy at West Virginia University. And he did his bachelor in mathematics and physics at the University of Arizona, and then his master's in physics at the University of Wisconsin, and then later his PhD in physics at the University of Maryland. And he is doing really interesting research that we will talk about here today. But before we start, I'll give Victoria the interview part that she came up with. So thank you, Victoria, and thanks, Paul.
All right, well, I'm ready to go. And Paul, it sounds like you are. Welcome, friends who are here and about to join us. Paul, thank you so much for bringing yourself and the work that you're about to present to us at Science Society. We really love to hear a bit about the background of the people who are joining us as guests. And so I'm interested to know if you can share with us something about your initial spark with respect to feeling connected to science, and maybe that happened in childhood or babyhood, wherever you can remember something that felt like a significant pull towards science. If you could tell us about that, please.
Yeah, sure. Very nice to meet you. It sort of happened organically when I was in elementary school and onward. I was always very good at math, and so I just, sort of gravitated towards math classes and things like that. And then took physics in high school and enjoyed it. And when I went to undergrad, I went there assuming that I'd be a math major. And I, when I was getting into like proof classes, I realized that what I liked about the math and what I was good at about the math was actually physics. And so that's kind of how I really went down more the physics side of things. And since then, it's just been, following whatever road, whatever road opens up.
Yeah, thank goodness that you were able to sort of look around and decide. And okay, so that road that opened up, can you take us along a journey and visit a few um, events that brought you up to this work that you're going to share with us today?
Sure, sure. So you mentioned I got my master's at Wisconsin, and then I ended up transferring to the University of Maryland for my PhD. And when I did that, I basically had to kind of start over in the research I had been doing when I was at Wisconsin. And I just looked around for different research areas, and I found plasma physics, but there was also a few others that I was kind of deciding between. And I had known a little bit about plasma at the time, but not much. And so uh, the topic that one of the researchers at Maryland was doing, which is called magnetic reconnection. If there's a chance, I'm happy to chat about it, but it's actually not the main focus of today's work. But I just thought it was fascinating, and so I started working with him, and I've been doing that kind of work ever since. Um, More specifically about this work, because as we'll talk about, most of it doesn't require anything about plasma physics. It's just that plasma physics helped us, helped provide a way to think about these things. And the reason we even started pursuing any of this research is in 2015, I think it was, NASA launched a mission that basically was the most amazing, had the most amazing instruments on it, that basically they took data about 100 times faster than any previous mission had. Um, and so it was just a complete game changer for the field. And I do theory and simulations. So um, it really became this challenge to rethink the way we think about the problems we were trying to solve and think about it at a much deeper level. And so that was kind of the start to get us thinking about the types of questions that I'll be talking about in the presentation.
Thank you. It makes it even more exciting. So then at this point, I will just permanently pass the mic to you for your talk. And then we have a room chat where friends in the audience can share questions for you that we can share with you. And also, if it's okay with you, bring some friends up at the end for a Q&A. Otherwise, the mic is yours.
Great. Yeah. No, that sounds great. And yeah, you have the slides. So I'll call out the slide numbers as we're going. And as we're going, if you need to interrupt with anything, it's totally fine. Just keep me where I should be.
Perfect. Sounds great. Yeah, that's really helpful if you're calling out the slide numbers and we can
Yeah.
follow along. So thank you.
Okay. So just the first slide here is just kind of a title slide. Specifically, it's got the names of my collaborators on this project. And at the bottom left, some acknowledgements of federal funding. So thanks to all of you for paying your taxes so that science gets supported in the U.S. And let's let's just go ahead to slide 2. So this is my conclusion slide, and I'll also put it up here as kind of an overview, summary slide. And so Katerina reached out when this recent study we did came out about a month and a half ago, and it got some coverage in the press. So there's a picture of it to the right there. But here's the big picture of what I want to talk about today. So the first law of thermodynamics basically describes conservation of energy, and it's been around for 170 years. And it's been known that the first law of thermodynamics formally only works, well, at least the way we often think about it, only works for systems that are in equilibrium. And I'll tell you what that means later. And so what we did is we did a theoretical analysis to derive an extension of the first law of thermodynamics that applies even for systems not in equilibrium. And so we call that the first law of kinetic theory. And I'll have to tell you what kinetic theory is. That'll come later. And the part that I'm excited about as well is I think it'll have a lot of applications in my own research area of space plasma physics. But I'm also thinking that it could be useful for other settings, so other physics settings, astronomy, chemical physics or chemistry, potentially biophysics, quantum mechanics, things like that. So at the end, I'll come back to these topics and kind of explore potential applications of it. So if we go to slide 3, this is kind of an overview of what are called the laws of thermodynamics. The way I like to describe it is that physics, I know that's a very diverse background for people here. So some people might be very experts in physics and some may not be, and that's totally fine. For physics, it's really kind of interesting. There's basically maybe, let's say, 20 or 25 properties of the way the universe works. And if you just know those properties and a bunch of math, you can basically recreate almost everything that's known about physics. And so of those 20 things, 4 of them are called the laws of thermodynamics. And This just kind of summarizes them. I will go through them in a little more detail, but putting them over here just shows you, we call them the zeroth law, the first law, the second law, and the third law. The zeroth law was added much later, which is why they didn't just call it the fourth law. They wanted to put it first, but there already was a first law, so they gave it this weird name. But in this presentation, I'm going to focus on the zeroth, the first, and the second law. I'm not going to talk about the third so much. So let's go ahead to slide 4. And in slide 4 here, I'm describing the zeroth law of thermodynamics. So what it tells you, the big picture is it defines what we mean by temperature, and it also defines this term thermodynamic equilibrium. So let's go through how this works. So let's say you look at the plot on or the sketch on the left. So you have a red block A, and think of that one as being hot. And you have a blue block B, and think of that one as being cold. And so when they're not touching, they're just going to sit there, and that's kind of all they'll do. But let's say you bring the two so they're in contact with each other. What will happen is that you get a flow of heat from A to B, and so the hot one gets less hot, and the cold one gets hotter. And eventually, if you wait a long enough time, they'll both reach a point where they're not changing anymore. And so when they're not changing anymore, that's what we call thermodynamic equilibrium. And when they're in thermodynamic equilibrium, there's a property of the two that's the same, which is the temperature. And so that defines what temperature is and what it means for it to be in equilibrium. Okay, and in this particular example, we call that global thermodynamic equilibrium because it's the same temperature everywhere. And there's something else called local thermodynamic equilibrium, which means it can be a different temperature at different places, but you still have something you can call a temperature. So that's the zeroth law. And if you move to slide 5 here, we have the first law. And so the first law, if you have some background in this, it's called, you can think of it as conservation of energy. Another way people talk about it is that energy can't be created or destroyed, but it can be converted between different kinds. And so this is just kind of the simplest way to think about it. So on the left, you have a picture of a balloon being squished. And so when you're squishing it, a few things are going on. By squishing it, you're doing what we call work. And so that's the blue term, dW there. So work just means in this setting that you're changing the volume. And what also happens at the same time is that the gas inside the balloon heats up. So when you squish a balloon, the gas inside will heat up. So you change the temperature, T, and we call that internal energy. So the fact that it's getting hotter means there's some internal energy there. And then the dq is the fact that we're putting heat in this case. So we're adding in this energy. And so what's amazing about the first law of thermodynamics is it basically says that whatever you put in, let's say you're putting in some heat, that same amount of heat goes into the work and the internal energy, and none of it disappears. You're not creating new stuff. It's just, whatever comes in has to get converted in these ways. And so I just made up some numbers on the upper right there. So let's say you're adding 6 joules of heat. And in this case, you're squishing the balloon, so the volume goes down, so the work is negative. So let's say that's -2. Then the first law of thermodynamics says, well, the amount that goes into internal energy has to be 8 in order for it to total up to 6, which is the amount that we put in. Okay, so that's the first law. And let's go ahead to slide 6 now, which talks about the second law. So the second law of thermodynamics is really interesting and weird and often misunderstood. There's this new buzzword here we have to introduce called entropy. But right now, we can just forget about the word entropy and just think about the big picture. So the big picture is going back to these blocks where you have a hot one and a cold one, and you put them in contact with each other. So we said earlier that there's heat that goes from box A to box B. And so the second law of thermodynamics basically says heat is always going to go from the hot box to the cold box, right? So you can't put the hot box next to the cold box and have the hot one get hotter and the cold one get colder. That's just not how nature works, right? Otherwise, you could, put your dinner in the oven and it would come out colder than when you put it in, and we know that never happens. So that is really what is meant by the second law of thermodynamics. There's sort of a directionality to things. And back in the 1850s, when people were studying this stuff, names like Carnot and Clausius, these folks, they came to realize that when you look at the heat that's exchanged in this process, if you write down this quantity related to how much heat moves over divided by the temperature, that quantity is always bigger than or equal to 0. And so that's equivalent to saying that the heat is always going from the hot to the cold. Okay, so in the 1850s, that's kind of all they knew about what entropy meant, and that's fine for our purposes right now. All right, so let's now move to slide 7, where we run into some trouble. And so, as I mentioned earlier, the laws of thermodynamics, the way we described it, only work in equilibrium. And so what does that mean? So let's go back to this picture of the hot block and the cold block. And you put them against each other and you get this heat flow across them. So what we said earlier is that if you wait a really long time, that everything will equilibrate and you'll have, everything's going to be at the same temperature. And that's great because that tells you what temperature is and you can measure it and all that. But now if you look at the middle sketch there in the purple arrow, let's say right when you take the hot block and the cold block and just have them start touching, right away, if you were to try to take, measure the temperature right where they're touching, you wouldn't be able to do it. It doesn't make sense to even call it a temperature. And you might think, well, that doesn't make any sense. You can have a hot block and a cold block and you put them together, it should be warm, right? Kind of in the middle. But it hasn't had time to get to the middle yet because that's the right sketch. So at the time of the middle sketch there, you can't define temperature in the standard way. And so that's weird because we're really used to things like temperature and pressure and entropy and heat and all these things. We're used to being able to describe these things, but even for this really simple system, you can't use thermodynamics for that middle part of the process. And so it's really disconcerting that there's 4 laws of thermodynamics and there's only 25 laws of physics that describe almost everything we know in the universe, and we broke them just by putting a hot block in contact with a cold block. So that's bad. So that's kind of the big picture of where we're going with this is we want to see what we can do to try to address these kinds of issues. So let's go to slide 8 and talk about how we start addressing these things. So far when I've talked about the first law of thermodynamics or any of the laws of thermodynamics, I haven't mentioned anything about what matter even is and the fact that like atoms exist. And so it turns out for a lot of thermodynamics, you don't even need to know that atoms exist. But we do know that atoms exist, and so it turns out that that's what we need in order to go past the laws of thermodynamics. And so the way it works, and this is a little tricky if you haven't seen this kind of stuff before, so I'll take you through it, is let's say you have the gas in the room that you're sitting in, and let's say you were able to measure the velocity of every single molecule in the room that you're in. And there's something like 10 to the 23rd particles in the room that you're in, so there's no way we could do that in practice. But it does turn out that we can measure this, not at the individual particle level, but kind of statistically. And so the idea is you can measure how many there are, let's say, going slow versus how many are going fast and things like that. And so we call that the distribution, or the distribution function, which is kind of a horrible name. But it's so we call it the distribution function of the velocities. and it tells you how they're distributed. So if you look at the bottom center plot there, this is the standard distribution of velocities that you see um, of, of the atoms or molecules when a system is in equilibrium. And so let's go through it a little bit. So right in the middle, you have v equals 0. And so this function, this distribution function, f, is relatively high there. And so that means there's a lot of particles that aren't moving very fast. And then as you go out to higher and higher velocities, you have fewer and fewer particles. And so when you go out to really high velocities, there are very few particles at very high velocities. And so this is just kind of the standard result that you get for systems in equilibrium. In statistics, we call this a Gaussian distribution. In general terms, we often just call it a bell-shaped curve. In physics, we tend to call it a Maxwell-Boltzmann distribution. And it turns out that the density is related to basically the area under the curve there. And the temperature is related to how spread out your distribution is. So in this example, you have two Maxwell-Boltzmann distributions, one with a temperature of 0.5 and the other with a temperature of 1. So the one with a temperature of 1 is broader, and so that means it's a higher temperature. And so the sketch we've been looking at is what a one-dimensional representation of the Maxwell-Boltzmann distribution is. Next to it, to the right, is what it would look like if you had 2 dimensions. So it's kind of spherical or circular, and in 3 dimensions it would be spherical. Okay, so all of this is because we're kind of measuring particles, particle velocities, not of individual particles, but statistically. This is called statistical mechanics. And so the idea is you have large numbers of particles, and you don't try to figure out what each one's doing, you just see what it's doing statistically. And in particular, because this system that we're looking at right now is in equilibrium, we call it equilibrium statistical mechanics. All right, so now so basically that kind of describes what's going on when you are in equilibrium. So if you move to slide 9, we can say, well, what does it mean if you're not in equilibrium? And so it's very simple. The idea is that the distribution of your velocities, your distribution function, is anything other than this Maxwell-Boltzmann distribution, the Gaussian shape. So anything else, then it's not in equilibrium. And it turns out you can't even really define a temperature or a pressure, or any of these things that we're used to. And so the area of study where you treat what happens when you have a distribution function that's not in equilibrium, that's called non-equilibrium statistical mechanics. And so it turns out there's tons of examples of things that are not in equilibrium. Maybe in the 1850s they weren't terribly common, but nowadays they're very common. And I'm going to focus on one set of examples, which comes up in my own research area of plasma physics. So let's talk about plasmas. So plasma is a state of matter, and so the ones most people are familiar with would be solids, liquids, and gases. So a solid, let's say you have a solid and you put energy into it, it melts and it becomes a liquid, and then you put more energy into it, it becomes a gas. And so the idea is if you keep putting more and more energy into it, at some point the electrons can come off of the atoms or molecules, and you're left with essentially a gas, but it's ionized, and so it's a charged gas. And so that's what is meant by plasma. It's totally different than the plasma that's in your blood. So I don't know. Unfortunately, they gave it the same name, but totally different thing. And so for plasmas, especially out in space, as we talked about, they have to be they're often very hot. And so if they're very hot, it turns out that, they're hot and they're not very dense. And it turns out because of those two reasons, it's very common for plasmas to not be in equilibrium. And so the stuff at the bottom here is to show you some examples of what some distribution functions look like in some plasmas. So let's start at the bottom middle. So this is an example from the solar wind. So the solar wind is the sun is out there in space, and it's basically nonstop just emitting plasma out into space. And so that's called the solar wind. And so it's made up of mostly protons and electrons. And so we can build a detector that measures distribution functions, put it on a satellite, launch it out into space. And these are some examples of results in the solar wind. And so if you look at the data, the top left one labeled D, um, that looks kind of round, right? Kind of looks like our picture on the previous slide of what distribution looks like in equilibrium. So, okay, maybe it can be kind of near equilibrium. But if you look at all the other ones, E through J there, those look totally different. So this shows that the plasma out in the solar wind, it turns out to very rare that it's in equilibrium. It's almost always not in equilibrium, and you have these really crazy shaped distribution functions. Another example is down on the bottom right. So this is data from a different satellite called Magnetospheric Multiscale, and this is the one I was describing at the beginning. So MMS, it's a NASA mission launched in 2015, and I'll talk about it a little more later. But the idea is if you look at some of these distributions that they have plotted in the red, yellow, green circles there, if you look at the red part, you see these kind of round shapes. They're not filled in circles like before, but they're just kind of like, we call them crescent-shaped distributions. And so those look totally different than, than the Maxwell-Boltzmann distribution. And so these plasmas are not just not in equilibrium, but they're really far from equilibrium. And so, again, in space plasmas, it's very common to not be anywhere near equilibrium. And then the final example I want to show you is on the left. So this is a picture from an experiment. My colleagues at West Virginia University have a laboratory experiment where they make plasmas. And they're really into Star Wars, so all of their devices are named after Star Wars characters. And so this one's called Phasma. And so that purple thing in the middle, that's a plasma. And what my colleagues do, they're experts at measuring these distribution functions. And in the lower left there, you can see some examples of some distribution functions they've measured. And you can see there's some tendency to look kind of like one of these Maxwell-Boltzmann distributions, but they also see features that are different. And so this is like hot off the presses. This is just in the last year or so that they've been able to do this. It's really opening up some new avenues to doing this kind of research because you can do it in the lab now. So again, the big picture, it's very common for plasmas to not be in equilibrium. As we'll talk about later, there's lots of other examples too. Okay, so let's move to slide 10 to talk about what we do about it. So once we know that we're not in equilibrium, how do we describe what's going on? And so the answer is this thing called kinetic theory. It's not a very good name, but that's what it's called, so we'll do it. And it's basically an equation that tells you how your distribution function evolves in time, even if it's not in equilibrium. And so the distribution function, again, is f. I put a little sigma subscript there because technically in a plasma, this can work for any species that you have, but I'm not going to get into that so much here. So just kind of ignore the sigma there. And so the answer for how the distribution function evolves in time was figured out by Ludwig Boltzmann in 1872. And you may notice that's almost exactly 150 years ago, about 150 years and about 5 or 6 months, actually 6 months, almost exactly 6 months. So it's been around for a while. It turns out this equation is horrendous. So if you're into the math kind of stuff, the reason it's so challenging is the right-hand side there has this quantity C of F, And that C of F is called the collision term or the collision operator. And it describes collisions between different particles. So the gas in the room, they're colliding with each other all the time. And so that's the term that describes it. And it can be written in terms of an integral. If you're really interested in it, it's that bottom right equation there. But the left side are all differentials. And so this equation contains both differentials and integrals. So it's called an integral differential equation. And they're really hard to solve. The good news is we believe the equation, and so it tells us how these systems work when they're not in equilibrium. If nothing else, you can plug it into a computer and have the computer do the hard work for you. But it's still really challenging to use this equation. But anyway, this forms the foundation of non-equilibrium statistical mechanics. So the next thing is really exciting here on page 11. So what I want to do is just show you a little bit about the second law of thermodynamics. So I'm going to focus on the first one, but I want to show you how the second law of thermodynamics was generalized for non-equilibrium systems. And this also goes back to Boltzmann in the 1870s. And the idea is this. So we know the second law of thermodynamics is that the change in entropy is greater than zero. And that's true when you're in equilibrium. And so what we said is, well, if you're not in equilibrium, then fundamentally your system has to be described by a distribution function rather than things like temperatures and pressures and whatnot. And so in order to see what happens when you're not in equilibrium, it would be nice to define entropy and to have that quantity be in terms of your distribution function. And that's what Boltzmann did. And so again, this word entropy is really weird, but the idea, the way to think about it, the way people use it, is you think of it as a measure of disorder. But I want to take you through just kind of the way to think about it. So if you look at the bottom right sketch there, you have what we denote as a box, and you have 8 black dots, and those, let's say those are atoms or molecules or something like that. And the arrows mean that they're moving around and bouncing and doing whatever they do. And then you have this partition in the middle of the box, and you can leave it open, right? And so at the time we're looking at it right now, there's 4 boxes to the left and 4 boxes to the right. And, that seems very reasonable, right? So if you kind of closed your eyes for a little while and let the atoms and molecules move around and do whatever they do, and then you opened your eyes and all 8 of the atoms or molecules are, let's say, on the left, you would say, wow, that's really surprising because it's kind of unlikely, right? And it may not seem too unlikely for 8 particles, but what if it was 10 to the 23rd particles? So it'd be really surprising to have 10 to the 23rd particles on the left and 10 to the 23rd particles on the right, and then you close your eyes for a while and you open it up and all the particles are on the left. It would be very, very, very improbable. And so the genius of Boltzmann was to say, well, we have this thing where it's very unlikely that all the particles are on the left. And we also have in the second law of thermodynamics that it's unlikely that if you put a hot object next to a cold object, that the hot object would get hotter and the cold object would get colder, right? We said that can't happen. And so Boltzmann linked the two and said that the entropy must be related to a probability. And so the probability is then related to the distribution function. And so, again, I don't want to do too much math here, but in the middle there we have the definition that Boltzmann gave of the entropy in kinetic theory. And all you need to know from looking at this is that the entropy S depends on the distribution function F. So he gave us a way to think about, if you know the distribution function, you can calculate the entropy, which again is just telling you how likely it is for that system to occur. And so what Boltzmann did, because he's a genius, said, well, let's just calculate how this entropy evolves in time. And he used the Boltzmann equation to do a calculation, and he used the collision term that he made up, And what he was able to show mathematically, no approximations other than making up his collision operator, that the entropy was always increasing. And so what that did is it gave a generalization of the second law of thermodynamics, but have it work completely well when you're not in equilibrium. And so this really generalizes um, the second law of thermodynamics to a non-equilibrium system. So this is kind of the backdrop for where we started getting interested in the first law of thermodynamics. And so for that, let's go ahead and go to slide 12. So we said the first law of thermodynamics was conservation of energy, where energy can't be uh, uh, created or destroyed. And so what in this recent paper that we did, we said, well, let's think about this not in terms of what we're used to thinking about it in terms of work and internal energy, the thermodynamic quantities. What we want to do is put it now in terms of the distribution function F, right? So in other words, when you squish a balloon, the question isn't anymore what's happening to the temperature, it's what's happening to the distribution function. And this is a very different way of thinking about it. So let's go ahead to slide 13, and we'll talk about a few ways to think about the distribution function and how it tells you something about your system. So the idea is that if you're given a distribution function, you want to be able to think about like what it's telling you. So what's the information in there? And it turns out that the reason we call it a distribution function in the first place is because it's related to the probability. And so we can borrow all these things from probability and statistics that tell us what to do with distributions to learn something from them. So for example, we use what are called moments of the distribution. And so there's a very nice analogy for this if you've studied classical mechanics. And it just, for example, like how mass is distributed, if you have a distribution of mass, right? So you can say, well, what's the total amount of mass? So that tells you something about the distribution. Another thing you could say is, oh, well, there's more mass to the left than there is to the right. So it's telling you kind of how the mass is distributed. And then you could say, oh, there's more mass further away than there is close by, things like that. So these are all related to the moments of, in that case, the distribution of mass. So we can do the same thing here in non-equilibrium statistical mechanics in terms of the distribution function. So again, if you're into the math, it's right here, but the short story is, even without the math, is you can say, well, if you have a distribution function, you can sum it up, and that tells you how much stuff is there. And so that's called the number density, and that's the 0th moment. The first moment is you take the distribution function and multiply it by the velocity, and then you integrate. And that's related to this concept of the center of mass, where you say, oh, there's more particles moving to the left than moving to the right, so there's a net bulk flow to the left, something like that. And then the second moment is you multiply by 2 powers of the velocity, and then you do your integral. And so that's giving you information about, how many particles do you have kind of further away, like fast ones. And then you can do it for the third moment and fourth moment and so on. And all these things are telling you something about how the particles are distributed in the distribution function. And so there's 2 key points here. One is that the concept of pressure and temperature and all those things, those only work when you're in equilibrium. But when you're not in equilibrium, you can kind of generalize the concepts of pressure and temperature. And so, for example, the second moment is related to the pressure and the temperature when you're not in equilibrium. But it's not temperature the way we're used to it from thermodynamics. And the second key point is that I just wrote the 0th, 1st, 2nd, and 3rd moments here. But you can keep going. So there's an infinite number of moments of the distribution function. And that's weird because when you're in equilibrium, the 0th, 1st, and 2nd can be non-zero, but the 3rd and beyond are all exactly equal to 0. So if your distribution is a Maxwell-Boltzmann distribution, all those higher moments are 0. So when you're not in equilibrium, it means that any of those other moments, an infinite number of them, can be non-zero. Okay, so let's go to slide 14. And here's where we start to address this question of what is the first law of thermodynamics telling us about the distribution function when there's some process going on. So there at the top, we have the first law of thermodynamics. So dW plus dE internal is dQ. And so let's just take these terms apart and see what they're telling us in terms of the distribution function. So the first one is work. So work is PDV, and as we said, it's related to squishing your balloon, right? So if you squish your balloon, you're changing the density of the particles inside the balloon. And as we said on the previous slide, the density is actually the zeroth moment of the distribution function. And so the work term, when you think about it in terms of the distribution function, it's telling you something about the zeroth moment. The next term, the internal energy term, we said that's related to the change in temperature. And we said on the previous slide that the temperature is related to the second moment of the distribution function. Okay, so the left-hand side of the first law of thermodynamics is telling you something about the zeroth and the second moments of the distribution function. All right, so here, let's go with that. So here's the fun part. We just said that when you're not in equilibrium, there can be an infinite number of moments, right? Any of these other higher moments can be non-zero, whereas they're all zero in thermodynamics. And so the point is that the first law of thermodynamics is only telling you about the zeroth and the second moment, and it's not telling you about any of the other moments. And that's kind of what's being left out when we're just doing an equilibrium theory. Okay, so we can kind of visualize this by thinking about, let's say you have a Maxwell-Boltzmann distribution, and look at what happens to the distribution when some of these things are changing. So on the top there, you have a Maxwell-Boltzmann distribution, and so let's say you're squishing your balloon, your density is going to go up, and so the colors there are supposed to be brighter. So the idea is that your density is higher, so your distribution function itself has a bigger value. The second moment, we said the temperature is related to the spread of the distribution. So it's as if you take your distribution and when you heat it up, you're spreading it out. And so there's a nice physical way to think about what's happening due to all the other moments of the distribution function. And the idea is, let's say you start with a Maxwell-Boltzmann distribution, then all of these other moments are describing the distribution function itself changing shape. Okay, and so that's kind of the physical way to think about it. All right, so now let's go to slide 15, and let's bring it back to the first law of thermodynamics just to really drive home what the issue is here, right? So the top part is basically what we had before. So this is the first law of thermodynamics in equilibrium, and this is where you squish your balloon, and you say, well, I put in some amount of energy, and some of that goes into work, some of it goes into internal energy, and if you add it all up, the amount that goes into work and internal energy is the amount that you put in. And all of that is great, makes perfect sense. But that only works when you're in equilibrium, right? So let's say instead, on the bottom there, you have your balloon, but instead of the gas inside, or maybe it's a plasma, instead of that being in equilibrium, let's say it's not in equilibrium, or it's not confined to be in equilibrium, right? So you still squish your balloon, you're putting in, let's say, 6 joules of energy, and let's say some of it goes into work, so let's say -3, and some of it goes into internal energy, which would be 7. And let's say, well, 2 goes into other moments, right? And so the idea is the 2 plus 7 plus -3 gives you 6, which is conservation of energy. And that's the way it has to be, which is great. The problem is the first law of thermodynamics only talks about the work and the internal energy. So if you just looked at those two, you would say, well, I'm putting in 6 joules of energy, and -3 is going into work, and 7 is going into internal energy. And you would say, well, that adds up to 4. if you didn't know about what's going on with the other moments. And the first law of thermodynamics doesn't know about the other moments. And so it's not that energy isn't conserved, it is conserved, it's just that we're not doing the accounting of all the energy that's there. Okay, so let's go ahead and go to slide 16, and this is for folks that like the technical stuff. If you're not into the mathy stuff, it's okay. Don't worry about this slide too much. But this in a slide is, in a nutshell, is just showing you the analysis we did to basically solve this problem. And so the idea is really, it's shocking. What I would call shocking is that in order to describe the conservation of energy, it turns out we have to go back to our friend the entropy. And it's not obvious at all why that happens, but here it is, right? So here's the entropy defined as before. So it's in terms of this integral of f log f. And the idea is we use this trick. And again, I'm not going to go into the mathematical details here, but you can basically decompose your entropy into a few different kinds of entropy, and I'm going to come back to what those things are. And the idea is you go back to the Boltzmann equation, and you derive an equation for how the entropy evolves in time. And you manipulate it in this crazy way, which I'm not going to go into details. And in the middle there, you can see there's these four terms involving these S's and J's and all that kind of stuff. And what we did with that is we realized that those four terms correspond to what we're used to, sort of, but these concepts of work and internal energy and heat. Okay, so let me take you through that just a little bit. So the first term is, it's basically the work, but it's a generalized work that allows you to not be in equilibrium. But otherwise, it's still just related to compression, squishing a balloon or something like that. The second term, we're calling the generalized internal energy. And the idea with that is it has two pieces to it. And one of the two pieces is the generalization of the regular old internal energy, right? So just the temperature part, but it's the temperature when you're not in equilibrium, if you want to think of it that way. But there's this other term that comes out of the math, which is what we call the relative energy. And as I'll show you in a few minutes, that is the term that describes all these other moments that were left out of the first law of thermodynamics. And it works very similar for the red term, the heat term. So there's just the regular heat part that just gives you what we're used to from thermodynamics. And then there's this other part that we call the relative heat, which is describing the heat associated with all these other moments. So the fact that you're not in equilibrium. And so that's what we're calling the first law of kinetic theory. For the experts out there, what's really neat about this is it's completely first principles. There's no approximations being made. It starts from the Boltzmann equation. So if you believe the Boltzmann equation, this equation is true. And the other great thing about this is that it's valid arbitrarily far from equilibrium. And the reason that's important is because there's been lots of work on extending the laws of thermodynamics for non-equilibrium systems. And most, if not all of them, let's say most, just to be careful, most of them assume that you're not terribly far from equilibrium. So you're doing like a perturbative approach. But this approach is completely nonlinear, so it's arbitrary. It works arbitrarily far away from equilibrium. And that's useful for plasma physics because we can be really far from equilibrium. So let's go to slide 17, and this gives a pictorial representation of what I was just describing to you. So let me take you through this a little bit. In the sketch on the left, this is just the regular first law of thermodynamics. So the blue box denotes work, the pink is heat, and the orange is internal energy. And so the black arrows just say when you have a thermodynamic process, you're exchanging energy between these three different kinds. And so the first law of kinetic theory is very similar. And so you still have a blue box, a pink box, and an orange box. I'm going to ignore the green box. If anyone wants to talk about it, we can talk about it. But just pretend the green box isn't there. And so you still have these arrows pointing between work and heat and internal energy. But what's different now is that the boxes for internal energy and heat can be thought of as having both kind of the regular internal energy and also a term for these other moments. And the same thing for heat. And so that's this kind of new approach, or this new way of thinking about it that we came up with. So let's go to the next slide, slide 18. And I want to talk through just a little bit about, how all of this works, like what's really going on mathematically and physically here. And so the term that really describes the energetics of the non-equilibrium aspects of your system, it turns out this quantity, we didn't come up with this quantity. This guy, Harald Grad, who is a giant in kinetic theory, was using this stuff in the 1960s. And so we borrowed the name from him. So it's called the relative entropy here. And the form is right there, and it's written in terms of an integral of f log f over fm. And the fm is a Maxwell-Boltzmann distribution. And so the idea is very simple. So if your system is in equilibrium, then your distribution is a Maxwell-Boltzmann distribution. And so f over fm will just be 1. And then you take the natural log of it, and it's 0. And so the relative entropy will be 0. So this is 0 if you're in equilibrium. And if your f is anything different than a Maxwell-Boltzmann distribution, then this quantity will be non-zero. And so therefore it's a measure of how different how far from equilibrium your system is. And it turns out this relative entropy idea goes back long before it was used in kinetic theory. So it was originally used in information theory. It's called the Kullback-Leibler divergence. And it simply is telling you how different two distributions are. And this came around in the 50s, and it turns out it's been used in all sorts of fields of science listed there. I'm sure there's more that I'm not including. And so, yeah, it took 15 years for it to be used in kinetic theory, which is really, I think, very interesting. And so the big picture is the relative entropy is a measure of how far you are from equilibrium. And so its time derivative is telling you something about how the energetics is going to change the non-equilibrium parts of your distribution function. So in other words, it's the energy associated with not being in equilibrium. And so the equation there at the bottom is how we link the distribution function to the energetics. Okay, so that's kind of the big picture. In the last few slides here, I just want to take you through a couple of things. One is I just wanted to point out when we derived this stuff, it was during the pandemic, during lockdown, and our first thought is, well, someone must have done this before. And so we looked into it, and sure enough, there was a study in the mid-1990s where they did all the same math that we did, and I don't mind telling you they actually did it better than we did. But it turns out that their interpretation of it was very different. They didn't relate it to the first law of thermodynamics at all. They showed it had some properties that they didn't like, but it's exactly those properties that we think are the most important ones because it's telling you what's going on with the energetics here, the story I'm telling you. And so things like that. So I thought that was just fascinating. The person doing this research was studying dilute gases in chemistry, so it's not papers. I don't usually read too many chemistry papers, so it's really interesting to see, how the same questions are being discussed in many different fields. So in the last few slides, I just want to talk about some potential applications. So let's go to slide 20. So I'm going to start with my own field of plasma physics. So as I mentioned earlier, plasmas are really hot. They're not very dense. And so it's very common for plasmas to not be in equilibrium. And so this analysis that we did, we think can be very useful for describing the energetics in some of these plasmas. And I'm not going to go into too many details. I have some backup slides if anyone's interested in sort of the details of some of these plasma physics things. But there are these processes called, there's one called magnetic reconnection, which is what I spend a lot of time studying. things like magnetized turbulence, shock waves, collisionless shocks, lots of things like that that we think this might be useful, because the big picture is we think there's this whole channel of energy that people haven't been looking at because we didn't know how to describe it. And I mentioned earlier this NASA mission, MMS, that was launched in 2015. So if you're interested in this, like I said, it's really amazing. They can measure data, 100 times faster than any previous instrument on a satellite. If you're searching around online, I was really lucky enough to be able to participate in the pre-launch press for it. So you might find a video with me in it from NASA headquarters and from the launch site the day before the launch and things like that. So it's really neat stuff. So I have a colleague that looks at MMS data, and so I asked him if he could calculate the entropy using the actual data. And again, I won't go into too many details, but sure enough, the answer is yes. And we compared it with some numerical simulations, and the agreement isn't perfect, but it's pretty good. And so it gives us the indication that we can use real data to study these types of processes that we're talking about. So if you go to slide 21, we can start going outside of plasma physics for some potential applications. So there's a couple in astronomy I wanted to point out, but the big picture is anytime that you have a system that is not in equilibrium, that you use the tools of kinetic theory, we're hopeful that this work that we've done could be useful to those systems. So one example of that is for stellar dynamics in galaxies. So in a galaxy, you might have millions of stars, and just like for the gas in the room that you're in, you can't keep track of what each atom or molecule is doing. Same thing when you have millions of stars in a galaxy, you can't keep track of all of them. And so one way to approach that is to study it statistically. And they use what's called the Jeans equation, which is just the Boltzmann equation applied to gravitational systems. And so because of that, we think the work that we did could potentially be helpful for studying those systems. Another example is people studying dark matter in astrophysics use the Boltzmann equation to describe the dark matter, so maybe our analysis would be useful there. And another example, which may be relevant, is in chemical and biological systems. So one example is what are called microfluids or nanofluids. The idea is you're passing a fluid through a region that's very small, so not too much bigger than the atomic or molecular scales. And so it turns out that in those systems, you can be away from equilibrium. It turns out the simulation techniques they use, molecular dynamics, there's a lot of analogies between that kind of approach and what we do in plasma physics. And so again, we're hopeful that the kind of work that we did might have something useful to say for those systems. And then finally, if we go to slide 22, if any of you are interested in quantum mechanics, like I said, we did this analysis during the pandemic. We had never heard of it. We wanted to see if anyone had done it before. And we had found that just not long before us, someone independently had done this for statistical mechanics in the quantum mechanical limit. And this is really fascinating stuff, but it turns out that there's, and this has been known, that there's, that you can do a quantum mechanical version of statistical mechanics. And what's the new part just recently is that you can define a relative entropy in the quantum case. And these folks, Florschinger and Haas, showed that you can derive something that looks like an extension of the first law of thermodynamics in terms of the relative entropy. So it's very much analogous to what we did. The interesting thing, though, is that in quantum mechanics, it's pretty challenging to interpret what's going on physically. And so we think that the analysis that we did and the fact that in classical physics it's much easier to describe what's going on physically, that we think some of the physics insights that we came up with could be useful for these quantum systems. And so with that, I will repeat the summary slide from before. Just very briefly again, so the first law of thermodynamics formally is general, but there's some issues with it, especially when you're trying to describe systems that are not in equilibrium. And so what we did is figured out how to generalize it for systems not in equilibrium, and we're calling it the first law of kinetic theory. And we're really hopeful that there's going to be applications. We think there's going to be a lot in plasma physics, but I'm hopeful that there'll be some of these other applications that I just mentioned. And so with that, I'll stop, and I just want to thank the organizers again for setting all this up, and to all of you for coming.
Well, thank you so much, Paul, for explaining us and guiding us through your work in a way that we can understand it and follow it. So thank you for that, and it's really beautiful work. I wanted, since you were comparing earlier to another work, and now that I understood that you kind of go into entropy, did you read about we had the speaker here, he published Zentropy. I don't know if you read that paper. It's from Professor ZQ Liu at Material Sciences at Penn State. So basically, he he labeled it Zentropy, where he takes into consideration, it's for material and for biological systems also, because there, for example, when you change the volume into a smaller volume, the entropy decreases, which has nothing to do kind of with the function of temperature. So he then uses stacks the different entropies from the different components of a system together, which kind of then creates a different entropy scales, and then he can sums it up with the partition function. I don't know if you heard about the work, but because you also take basically this, if I understood it right, also the volume or the pressure into consideration, right?
Yeah, so I had not heard of this, so I'm really fascinated by it. I just pulled the page open on my computer, so I'm going to check that out afterwards. It sounds really
Yeah,
interesting.
he gave a really long talk here, um, and he also has a YouTube channel where he shared the talk combined with the slides. So
Uh-huh.
if you check his name out on YouTube, he's really good. He has a lot of followers on YouTube,
Uh-huh.
and he explained it really well, and it was fun listening to. But then we had a very long discussion, so the YouTube part probably is more condensed than has the slides. So
Neat. Yeah,
yeah,
I'll check that out. Thank you.
yeah, it was a really good talk. And Lisa, you just joined. I wanted to give you an opportunity to ask questions so I don't take over. Thank you.
Oh, yeah, thank you so much. This was a fascinating presentation. I have about a billion questions. I had been following, there was some work around black holes and plasma jets that seem to implicate this sort of phenomenon, particularly at the outer ring. And I believe this is also related kind of to the concept of Alfvén waves and potentially where the plasma jets on the sun are coming from. So, yeah, do you think this will have practical applications for our ability to understand and, prevent catastrophic solar flare damage?
Oh wow, great questions. Yeah, so you're totally right. So it's definitely, yeah. So they have these beautiful images of the black hole, the center of the galaxy, and um, the images. Of course, I mean what we're seeing is light that's coming to us through a plasma, and so there's a number of people, and we call it. It's sort of a subfield of plasma physics called plasma astrophysics, that look into using astrophysical data and our knowledge of plasma physics to see if we can understand what's going on out there. So it's a very active, thriving area of research. It's very fascinating. Going on to the second part of your question about solar flares, so that is an area related to my own usual research when I'm not doing thermodynamic stuff. And so solar flares are related to this uh, process called magnetic reconnection. So that's the stuff that I do most of my work on. I can answer. I can go into into depth if you want, but I'll start just sort of big picture. That where we are with solar flare modeling is we have a pretty good, if you show us a picture of the sun, us meaning people that do this kind of research, which isn't necessarily me, by the way, but if you show people a picture of the sun, with pretty good certainty, they can say, okay, well, there'll be an eruption over here. The tricky part is being able to say when it will happen and, like where the sun is in its rotation. So maybe there'll be an eruption, but it'll completely miss Earth. And so maybe we don't care so much about that, right? But it's really hard to be able to say, okay, there'll be a flare in this region, and the stuff that comes from that flare will come out and hit us on Earth. So that's a really tricky part. And the other tricky part is that, so you can't, since we can't predict in advance, oh, there'll be a flare there in 2 days, the way it works right now is you just kind of look to see when a flare happens. And the light gets to us very quickly, right? The sun's like 8 light minutes away, so we find out 8 minutes after it that the flare happened. But the plasma goes much slower than light does, and so it takes about a couple of days for it to get here. And so by seeing when a flare happens, it kind of gives us a couple of days of warning to know that, well, okay, maybe this stuff will run into Earth and maybe it'll cause some problems. And the good news with that, too, is that there's a number of things that people can do when they know that this stuff is happening to try to minimize the damage. So, for example, satellites can be affected by, this is all called space weather. So satellites can be affected, and if they know it's coming, they can kind of shut down and go into what's called safe mode, so that the circuits don't get destroyed when a solar storm passes. So things like that. Same kind of thing with like the power grid. You can basically shut down for a little bit and avoid major damage if you know it's coming. But you're totally right. We're not to the point of being able to predict space weather the same way that we can predict the regular weather. And so it's still very much an active area of research. And it's a really important one, too, because you can have flares of lots of different sizes. And so the small ones don't affect us too much. But if you had a really big one, like insurance companies have looked into this, and they estimate that if a really big flare hit, it could cause like $6 trillion of damage, and it would take months to recover from it, and those are all bad numbers. So the more we can do to predict that stuff, the better. Does that answer your question?
It did. Amazing. And I have one follow-up that, okay, so the magnetohydrodynamics and the relationship between the acoustic aspects. It seems to me there is a bit of, there's been all this talk of phonons and ways of dispersing energy and potentially curious findings and, missing energy, or it seems like it's a similar thing. So do you have any opinions on that, or these kinds of, acoustic electric analogies, or does this relate directly to the out of equilibrium sort of systems that you study?
Wow, cool question. So it's funny when you bring up MHD, magnetohydrodynamics. One of the first things I learned about plasma physics when I was in grad school was there was a book that said something like, it was a introductory level book, like a 100 level book, that just mentioned magnetohydrodynamics and said something like, but it's really hard. And now I do plasma physics, and magnetohydrodynamics is kind of the simplest thing that we do to describe a magnetized plasma. So when we do magnetohydrodynamics, we're basically assuming that the system is in equilibrium. And so the stuff I talked about today is out of equilibrium. So it's stuff that's so complicated that even magnetohydrodynamics just doesn't do a good enough job to describe it. Of course, magnetohydrodynamics is useful for lots of other things, so it's not like it's not useful. And coming back to your question about the acoustic analogy, so yeah, so magnetohydrodynamics, so for those that don't know what it is, it's basically like hydrodynamics, but you include a magnetic field for a plasma. So hydrodynamics is just the regular, the way you describe a regular fluid or a gas. And so just like a regular fluid or a gas has acoustic waves or sound waves, there's an analogy to the kinds of waves that you get when you have a plasma there. And so those are called magnetosonic waves because you get the magnetic field playing a role, and you're also getting the sound wave part. And so, yeah, those waves are all over the place. You can detect them with these satellites, like out in the solar wind and things like that. So, yeah, it's good stuff. Does that answer your question?
Yes, I have many more, but I'll let someone else ask if they want. Thank you so much.
Yeah, thank you.
Yeah, thank you. Ethan, do you want to go ahead?
Yes. I have a question, statement, something like that. I say it with a great deal of trepidation because I'm not sure I understand it. But it's, is this similar, or I want to Jarzynski's equality? Are you familiar with Jarzynski's equality?
I don't think I am.
Okay.
What is it?
I think it's very similar to what you're talking about. It's used, I learned about it in Nicole Halpern-Younger's work, and people trying to do one-shot thermodynamics, as they
Okay.
call it, trying to improve the understanding of thermodynamics at the quantum limits. I
Okay.
could post maybe a picture here of the equation. I don't know, and I just get maybe a sense here that maybe it's a different mathematical structure for a similar equation, but perhaps, I mean, it's definitely part of non-equilibrium thermodynamics that they're trying to do.
Uh-huh.
So I don't know if you can see my PTR photo there, if that makes any sense to you right off the bat.
To
The
refresh,
terms,
you just pull
yeah,
down the screen, and then it should refresh his
yeah,
picture.
Oh,
And then you can click on his profile.
okay.
Click
yeah.
again on the picture, then you should see it in big.
Okay.
But I think maybe the difference might, I think what you're talking about is similar, although they're definitely both in non-equilibrium systems. But as you mentioned something about yours was in far from equilibrium rather than from very close to or near equilibrium.
Right.
I think this is kind of, talking about Prigogine and perturbative systems, but I'm not
Right.
sure. That's why I say this with a great deal of trepidation, but I do think there's a lot of connection here to what you're
Okay.
talking about.
Great. I'll look into that too. Yeah.
Does,
And I didn't really convey this too much in my talk, but there's been, lots of work on non-equilibrium statistical mechanics. So it's not like we're the first people to ever do anything on these problems. But yeah, so this is great. Thank you for
Yeah, so I
sharing that.
mean, this is kind of known in those circles as, instead of having an inequality, that they got to an equality on this, in terms of thermodynamics.
Mm-hmm.
Yeah.
And I think it's related to like fluctuations as well, which is,
Yes, absolutely.
yeah. So, and in our work, we didn't have to put it in terms of fluctuations, which doesn't mean it's good or bad. It's just, I think that makes it different. But I'll be interested to look into it a little more and see what kind of if there's links between them. Yeah.
Yeah, thank you. Kirko, did you have a question?
Yeah, mind you, I know very little about like physics in general. I've never taken a physics class. Um, so like I kind of somewhat understand like most of your research has been with like non-equilibrium systems, but I'm kind of curious how because like oh, how do I say this question? So you know like superfluids, right? Like they're
Uh-huh.
really cold,
Yeah.
and for some reason they do like super weird things. Like
Yeah.
they'll do an action where it's like, well, there has to be energy to to carry out this action, like climb up the sides of a
Yeah.
container. Like, so I was
Yeah.
kind of wondering if your model kind of fits something like that because like, you would think that like the colder like the system is, the less energy would be available to do stuff. And if it's a superfluid, it's got to be pretty darn cold.
Yeah.
So I was kind of, you know what I'm saying? I was kind of curious on if like I guess your model could extrapolate towards that end of like what's going on here.
It's a great question. So superfluids are just a little bit of background for those that aren't familiar. So superfluids are these they're fluids, but they take place, as you said, at really low temperatures, and so the properties of quantum mechanics become so important that they actually change things on the macro scale. And so yeah, you get these weird things like fluids kind of crawling up walls, and essentially the viscosity can become essentially zero, which is amazing. So can our work be useful for that? I would say right now no, but maybe with some work we can try to figure something out. The stuff that I did is purely, or that we did is purely in the classical limit. And right at the end there, I mentioned that there's some folks doing quantum statistical mechanics. And so I think you would have to go more into that realm in order to describe superfluids. In case you're interested, though, it does turn out that there's some really interesting relations between superfluids and the stuff I usually study in plasma physics called magnetic reconnection. And the idea is that when you get superfluids kind of, let's say, rotating in a circle, we say that the word we use for that is vorticity. So you have a superfluid that's kind of going in circles, and it turns out that the vorticity acts a lot like the magnetic field does in a plasma. And so I study this process called magnetic reconnection, which is where magnetic fields, think of it as breaking. And it turns out that in superfluids, the lines of the vorticity break, just like magnetic fields in a plasma do. And there's some really neat videos online of experiments in the lab where they have superfluids and they put in these tracers so you can actually see it. And you can see these vortex tubes essentially breaking and reconnecting. So it's really cool stuff. So there's analogies with superfluids and plasmas, even without the non-equilibrium stuff, which is really neat, I think.
Super cool. Thanks, man.
Yeah, thank you.
Yeah, thank you. I wanted to go back to the black holes work that was shared here a few days ago, where they saw where their theory, their calculations kind of matched that there are kind of spikes around black holes of dark matter that kind of drag down then some stars around them, and then there's kind of this no, I don't know, I kind of understand that's not an equilibrium, so if one get dragged in and slowed down and the other one gets more um, but gets more mass, as far as I understand, and you see this peaks. So is that also a system, around black holes and this dark matter interaction, where there are kind of peaks of dark matter around those black holes? And could you calculate that too, or because you talked about objects in the universe and how to apply this theory.
Yeah, no, it's a great question. I wish I knew more to be able to answer it better. Um, but I think what you're saying is definitely correct, and the extent of what I would say the extent of my knowledge is that I know that people do use the Boltzmann equation to describe dark matter, and so because of that, it's possible that what we're talking about would be useful for them. It's something I've just kind of just barely scratched the surface on to just know that there might be these analogies, but I haven't yet been able to dive in deep to that to give you a better answer to your question. So sorry about that.
Yeah, I'm sorry that I'm explaining it so bad. Like they
No, you.
found their data really, like their calculations really correlated well with the data that was recorded, that there's kind of density spikes around black holes, and then they create this dark matter, then creates this dynamical friction to a companion star. So one star gets dragged really strongly. So it sounds like there's not an equilibrium, right? That there are these local spikes that
Right.
can locally on one star have this effect and a completely different effect on the companion star. So I
Right.
thought that's where I thought the non, but maybe I'm oversimplifying things.
No, I think you're right, and I think that in terms of the Boltzmann equation, I think that would be described both through the forces, like the force uh, term that you include in the Boltzmann equation, and in the collisions. And so I think like that's so yeah, it yeah. I think you described it very well, and I think you're right that it's not in equilibrium. Um, yeah. So,
Yeah, I mean, yeah, if you want to look it up, it's in our very recent recordings, Manho Chan, and yeah, dark matter density spikes is somewhere in the title. But
okay.
also, when you look for the paper, if you look for black holes and dark matter density spikes, you will find it. I think it was just yeah, just recently published. So,
Great.
yeah, I think it's really interesting, and it was so fascinating how it really matched well the data. So I was thinking about. Um,
Great.
Kiko, did you want to add some?
Yeah, I actually just randomly came up with one more question.
Yeah.
Okay, so like you were saying like how a lot of your research had to do with like magnetic reconnection lines.
Yeah.
And I'm just trying to make sure I understand like those are like so like think about like the Earth magnetosphere. Like the reconnection line is like when like let's say like we get hit with like some type of like blast charged particles, like one of the lines breaks like at one point and reconnects like on the other side of like where that wave came from. Is that what you mean by reconnection lines? Just
That's
so I can.
exactly. Yeah, that's
Okay, sweet.
exactly right. In the slides that I have, if you skip ahead to slide 25,
Mm,
there's a little picture of it, or not a picture, but a sketch, kind of exactly what you just described. So I'll just take you through it real quick. The light blue lines or the white lines represent magnetic fields, and
mm,
they're pointing in opposite directions above and below the center there. And then the rectangle there is where magic happens. And if you're interested in details, we can talk about it. But the idea is just like you said, the magnetic fields above and below. You can think of it as though they break and kind of cross connect to the other side. And then you have these magnetic field lines that are very strongly bent. And magnetic field lines kind of act like rubber bands. So they'll shoot out to the left and right, and they'll take the plasma surrounding them with it. And so when the plasma comes out, it's moving really fast and it's heated by the magnetic fields. And so this is a process that converts energy from the magnetic field into the surrounding plasma. And so this is what's going on during a solar flare, where you release lots of magnetic energy really quick. It happens in, as you said, Earth's magnetosphere, so the region of influence of Earth's magnetic field. So it's called, those are called geomagnetic storms or substorms. And so When you see aurora, if you've ever seen aurora, you're not seeing reconnection, but you're seeing the after effect of reconnection, because reconnection happens in Earth's magnetic fields and drives this plasma towards Earth, where it ionizes the atmosphere, and the de-excitation of the gases up there is what you see as aurora. So that's just a couple of examples of where reconnection's important.
Sweet. So my question is like, it's like, at least from my understanding, like the hotter, the denser the material, the spinning material, the stronger the magnetic field it can create. But like, at least from my understanding, also like black holes also have like magnetic fields,
Yes.
but like it's also like from my understanding that we believe black holes to be cold. So like,
Oh.
how does that like I guess like, the real question, let me not get into too many questions, but the real question is that also like regardless of the temperature of the black hole, does that mean that like because black holes can also have like magnetic fields that like they can also like have like that same thing happen where they can break off and reconnect uh uh a field line, or I can't remember the term you used,
Yeah.
because then that
No,
would
that's right.
like also cause like the shoot off of like, you know what I'm saying, like some type of like charged particle or whatever,
Yeah.
because that would be huge, right? If it's from like, let's say like the center of our own black hole, you know what I'm saying?
Yeah. Yeah. So instead of talking about black holes, I want to talk about some other objects, because it's easier, or people talk about this stuff not so much for black holes, but for other things. Um, so there, so there are things called neutron stars. So what a neutron star is when you have a star that's massive enough, and when it runs out of its fuel, it undergoes a supernova and basically explodes. And what's left over is essentially nuclear matter, right? A star made of completely, nuclear density of matter. So, and that's called a neutron star. And the way to think of it is that, like the sun, for example, it rotates, right? And so whatever star was there before it underwent a supernova was, presumably rotating. And then when it has an explosion, it throws all this mass away, right? And so just like, figure skaters, right? When you have, stuff, your arms out, you rotate pretty slowly, but when you pull your arms in, you start rotating faster. So these neutron stars just are rotating incredibly fast. And because of that rotation, the magnetic field, it gets stronger. Um, and so for the sun, for example, the magnetic field is maybe, let's say it's about 100 Gauss or something like that, or 1/100th of a Tesla, if you prefer those units, whatever. But it doesn't matter, let's just call it 100 Gauss. And so these neutron stars can have magnetic fields of like 10 to the 12th Gauss, so like a trillion Gauss, so 10 to the 10 times more strong. And so if you picture like a solar flare happening, but not on the sun, but in one of these neutron stars, because the energy goes like the magnetic field squared, it's about 10 to the 20 times more energy is released during these things. So it's, as you said, it's just these huge explosions. And there's these other, a class of neutron stars called magnetars. And these are ones that have an even stronger magnetic field. And the magnetic field is so strong that it, like quantum mechanical effects start taking place. And so those are called magnetars. And so there are people that think that we can detect flares on magnetars, which again are even, it's about 100 times, or 100 or 1,000 times stronger magnetic field. So, another million times stronger for the solar flares, or for the flares on a magnetar. So the short answer to your question is yes, absolutely. It's pretty well agreed that these types of explosions can happen on what are these compact objects. Um, and it's still also an active area of research too. So yeah, really cool stuff. Yeah, thank you.
Yeah, thank you so
Yeah.
much, Ethan. Oh, did you want to? I
Yeah,
wanted to
yeah.
just ask Paul how much time he has left. As I've been here for an hour and a half, I wanted to make sure we don't take too much.
Yeah, and I can answer some more questions.
Okay, great. Thank you.
Yeah, I was just wondering if you had mentioned earlier about talking about this in terms of information, and so I was thinking, I'm very interested in classical information and quantum information theory and kinds of things
Oh,
I think about. And
okay.
so I'm wondering if you just maybe speculate or think about and focusing on the information side of this from that perspective, what you see it doing, what it might be valuable for, and maybe in terms of understanding something like, information processing, getting chaotic in the classical limit, or something like that, or being able to, figure out some boundary between, computation suddenly getting chaotic, or in terms of, these things, information engines, using information to create work. Just, maybe just gets your wild, sci-fi even speculations or thoughts on that. Yeah.
What a really cool question. I wish I knew the answer. So, what I learned,
That's why I want you to
I knew a little.
speculate. I'm not looking for an
Yeah, right,
answer. Just a general,
right, right. Yeah, but what I can tell you is this: I knew a little bit about information theory before I started this, and one of the things that I thought was so surprising is that this, relative entropy concept, came from information theory, and so I think in many ways, what the information theory was kind of more mature on these topics than the physics was, and so in a sense, I would say that what we're doing is kind of I would say this work that I shared today is a step towards us kind of catching up to the information theory people, because they've been doing this for years, right?
well,
And
that's, it's interesting because it brings up a lot of interesting history, right? Because
yeah,
Clausius and then Boltzmann were doing a lot of stuff without realizing they were talking about information,
right,
right? And then Shannon came along and talked about information, but didn't really relate it to what Boltzmann and Clausius and maybe von Neumann kind of was, So I think this is currently what we're working through as a,
yeah,
community of human beings,
yeah,
where this leads. So I think it's, I don't know that one's more mature. It's just sort of noticing this connection now,
yeah,
and now that, there's a classical version simultaneously with knowing that the quantum version is more complete, but not knowing what that is. So it's
right.
all very kind of interesting and puzzling at the same time. But
Yeah, yeah.
yeah.
And you mentioned Shannon. Shannon, big contribution was talking about entropy for information, and really linking those two areas, which is amazing stuff.
Yeah, I often come on and say, like, that regardless of your particular choice or definition of entropy, that it's essentially, a simplified way of talking about it is that it's hidden information, and its unit is bits.
Uh
But
huh.
I think sometimes I get a lot of pushback for a statement like that.
Yeah.
So yeah.
Yeah.
I know somebody previously raised a hand, but I didn't realize, and now I don't know who it was. So if you still want to raise your hand and ask a question, please please go ahead. I wanted to go back a little bit to if you have like a couple of minutes to biological systems, or maybe engineered biological systems. How? Oh, Ethan, did you had
No, I was
something?
just clapping my hands. Yeah, I was
Oh,
going to get to a little bit of that about maybe epilepsy and information in brains, and that was kind of,
yeah.
without stating in this, I was kind of, would there be what he was talking about, some application to understanding in a big way what's going on in epileptic seizures or something in brains, from,
Yeah, or doing sleep,
yeah.
and then if you could if one could then maybe, well, also design, there's a lot of designing of like organic robots and non-organic tiny robots. And do you think this would be helpful to come up with design that makes more sense. And also adding to that, since we are also talked about the information theory and so on, for maybe a AGI system, do you think it's this can help to make this transition to where, knowing better our thought process and then translating it to an artificial one?
Wow, I mean, just amazing questions. um, I'm gonna admit, these questions are really far from the types of things that I typically think about. But one of the things I've been excited about this research about, or what the reasons I've been excited about this research is that um, I I am hopeful that it could be useful for other fields. Um, my initial thought to your question is that really, I don't, I don't see anything obvious that where this work could, do something that that isn't being done already. So I'm doubtful, but it's something I'd be very interested in learning more about. I did get this opportunity, and just coincidentally, it'll be next week. I'm going to a conference where they're taking a bunch of plasma physicists and a bunch of biologists and basically just putting them in the same room and saying, hey, teach each other and learn from each other and see if, insights that, one of your communities has can help the other community and vice versa. It's an NSF, National Science Foundation funded um, thing. And so, my knowledge of biology is pretty slim. So I'm just excited to go there and just kind of learn what's going on, what kind of things people are talking about, and just explore avenues if any of the things that we've learned is useful for them and vice versa. So I wish I could give you a better answer, but I think these are all really neat questions, and hopefully, people will continue to think about these things.
Yeah, thank you for that. And yeah, this will be for sure interesting to have that exchange. That's wonderful
Yeah,
that will happen. So yeah, I'm curious actually to hear. You should like tweet about it or something. I don't know.
yeah. I know for me, it's so easy, and I would say even kind of normal to just, we have the one thing that we're thinking about, and we kind of often just push forward on that, and it takes being jolted out of that to say, hey, let's think about things more broadly and cross-disciplinary. And yeah, so it's neat that things like that are happening.
Eli joined the stage, and then Dr. Brown. If you have time for two more people's questions, go ahead.
Sure.
So thanks. Really, actually, a couple of comments. One to Paul and one to Ethan. So Paul just kind of wanted to say, I see what you did there. First law of kinetic theory. Nice move. I like that.
Thank you.
And so Ethan, regarding the the pushback on bits having energy or even entropy, because that actually entropy describes the flow of energy, right? um, it becomes very straightforward when you think about it operationally, in terms of either what is the energy going to be to set or reset a bit, but have it remain stable so that it's useful information. So you can't have thermal energy jostling everything around, because that would just wash out your bits and you wouldn't call them bits. So if they're bits, then it has to take a certain amount of energy to write them, and a certain amount of energy to erase them. Um, Also, it relates in a very straightforward, simply to Boltzmann's definition of entropy, because if you have your memory array written with the Magna Carta or what have you, that is one very specific combination compared to the randomizing all of the bits. And so both of those things relate to the energy of bits.
And there you're talking about more of a classical
Yeah,
description, right?
exactly.
Yeah.
It'd be interesting if like any of the higher order moments could be related to that, or maybe use some the same formalism of those higher order moments as to describe the thermodynamics of computation.
Yeah. When you talk about it in quantum, you get some weird possibilities too, in terms of negative temperatures relating to it. So there's all sorts of stuff that I don't have quite a handle on yet, but I'm getting there.
Paul, I don't know, you're muted. I don't know if you. Oh, there we go. If you wanted to add something or say something.
Oh, no, nothing to add. That's great.
Yeah, thank you for adding that. And if nobody else, Dr. Brown, he left, but if nobody else has questions right now or comments, oh, Elizabeth wrote in the chat. Sorry, I didn't see that. Um, How should high-frequency radio operations apply this work to constructing an antenna, especially BRT solar wind turbulence, as shown on slide 27? Oh, Elizabeth, I'm trying to bring you up so you can ask the question.
Slide 27.
She said she can't come out yet. I tried to.
Okay, well, I can try to speak to that. Um, if I interpret it correctly, the question is how can we measure this stuff basically in turbulence in the solar wind? And that's a fantastic question. And so the NASA mission that I mentioned, MMS, it can measure distribution functions, and like it said, it measures them about 100 times faster than any previous um, uh, satellite mission, but it's actually not all that great in the solar wind. And that's because the density is very different, and so the instruments aren't optimized for operation in the solar wind. And so one of the things, there's a new mission that is under development called Helioswarm, and the idea is to send a whole bunch of satellites out there and to make the detectors so that they are sensitive to the types of densities that you get in the solar wind. And so I don't think they're going to measure distribution functions as fast as they do with MMS, but they'll measure them more accurately for the solar wind. And so I think if I remember right, the launch date is around 2027. And so anyway, so that's going to be a great example of a mission. And because they have, I think it's 9 different satellites, and what they'll be able to do is compare what they're measuring with the different satellites, and that will give a lot of information about the properties of the turbulence in the solar wind. And they will be able to measure distribution functions and therefore measure some of the non-equilibrium effects that are going on. So I don't know if that totally answers your question, but the short answer is that people are already on this one, and should be some exciting things coming down the pike in a few years.
Yeah, thank you so much. I'm sorry, Elizabeth, it's not working to bring you up, so I hope it answered your question. If not, I'll reply in the chat that there's still something that you needed answering. And yeah, I think we've been going almost for and Mustafa asked, I think you already answered it, but just to read out this question, are you the first to have addressed these mathematical equations? If not, who found them before, and what interpretation did they give them? And could they have other interpretations in the future?
Yeah, thanks. Yeah, so I mentioned that we found this paper from the mid '90s that did the math before us. I'm unfortunately don't know how the name is pronounced, but the last name is EU, and so they did the math, and the I think the reason for the big differences in interpretations between what they were doing and what we were doing is that they were thinking about entropy the way everyone thinks about entropy, which is from the point of view of the second law of thermodynamics. And so, and the other aspect of what they did that was very different than the way we were thinking about it is that they were trying to come up with this a description of a non-equilibrium system, but that you'd be able to use in the same kind of analytical techniques that you do for an equilibrium system. And the short story is they were unable to do it. And they kind of said they kind of said, well, it doesn't work the way we want it to, so we think we should use this other quantity instead. And for in our analysis, we recognize that the types of quantities that come out of this analysis are related to the things that we're used to in thermodynamics, and that it's actually a feature that it doesn't, you can't write it in the same way as thermodynamics because it's not a thermodynamic system. It's non-equilibrium. And I think the other part of that what we did that was really different was that the way we decomposed the entropy into these different components, it's that decomposition is what led us to the fact that some of these same thermodynamic quantities were actually coming out of it, and that's obscured without doing that kind of decomposition that we did. So I think the last part of the question is just, are there other openings for interpretation? Absolutely. I think that's one of the great things about science is that, two people can see the same thing and have very different interpretations of it. And so, and I'm really excited also that there's this quantum mechanical picture of the same kind of a thing. Short stories. I think there's lots of ways to that all this work.
Yeah, thank you for asking the question and for sharing that. I think this was a really interesting discussions, and maybe we run a little bit wild on the applications for the future, but who knows? We'll see. It will be really interesting to learn from you in the future what you your collaborations in the future and what comes out of it. I think it's really exciting. So yeah, congratulations and all the best for your future work, and we for sure will be following it. I hope you enjoyed it, and thank you so much for coming today.
I did, thank you, and I mentioned to you before, but thank you again for all you do and for making a forum for people to talk about science and such an interdisciplinary way. I think that's so fantastic. So keep up the great work.
Well, thank you. That's so nice of you. I really appreciate it. And thank you everyone for coming and participating and asking questions. I think it makes the discussion and the directions we go in then way more interesting. So it's really that makes this club so interesting. So yeah, thank you for coming and adding your knowledge and your questions and comments. And I hope I hear you all back again soon. We have a room again next week about Dr. Olgin and how faulty energy production in the south of the heart, the mitochondria, how they kind of perform, are a really good early sign of heart failure. And I think it's a really interesting work that will have a really good, new diagnosis tool to prevent heart failure, hopefully. So yeah, if you're interested in that, join us again. And thank you, Paul. And yeah, enjoy the rest of your day, afternoon, evening, wherever you are. Thank you. Okay, I'll close the room in 3, 2, 1. Bye, everyone. Thank you.